Welcome to lecture 23 of Power System Protection course. In the last lecture, that is lecture number 22, we discussed about the transformer protection, and in that we discussed about the incipient faults like interturn faults and the faults due to overfluxing, all those faults, and also we discussed how incipient faults can be protected, and from that how the transformer can be protected using the non-electrical approach, that is the Bucco's relay. Then for overfluxing, there is another kind of relay, that is V by F relay. We call it voltage per hertz relay. That is also one of the important relay. And now we can see the little bit, we can summarize what we discussed in the last class. This is the transformer protection application chart, right? So in this we can see gradually if we categorize the faults in transformer, there are two types: internal faults and external faults. So under internal fault category, if we'll categorize, under internal fault we'll have phase faults, ground faults, then your interturn faults, right? Okay, then your tap changer failure, then leakage of oil from tanks. So these things can be covered, these things can be protected, like for using the different protection schemes. Already we discussed those schemes in last classes, in the previous classes. So external faults consisting of system phase faults, then system ground faults, then your overloading condition and overfluxing. So all these aspects we have discussed, and how we can protect already we discussed. Here we can see the various protection schemes, and here we have different types of faults. So for phase faults, as primary protection, the percentage differential relay is being used, and for backup protection, overcurrent or distance relay is being used. Similarly, for ground faults, the same schemes are used, like percentage differential relay as primary protection, and your overcurrent or distance relay as backup protection. But for interturn faults, it's an incipient fault, therefore the Bucco's relay is being used, and oil leakage also Bucco's relay. Similarly, overloading condition, for overloading condition, overcurrent relay with thermal image of the protected unit, that is this. So we have not discussed this thermal image of protected unit, because this is not coming under your syllabus. So only overcurrent relay we discussed. Then overfluxing we talked. Overfluxing means it is a very different type of relay that in fact detects the V by F ratio. We have seen how when the V by F ratio lies within a particular range, operating range, and then your relay operates. Now your transformer protection is over almost, and we saw that how differential protection scheme plays very important role in transformer, and it in fact used as the primary protection scheme for transformer, and for some other faults the other different types of schemes are used. And here we will see that for busbar protection also the differential protection scheme plays very important role. So let us first discuss what is a busbar and how in fact it plays important role, how it plays important role in a power system, and why it needs in fact the protection scheme, whether it is essential to protect the busbar. So here you can see the bus bar structure, right? In fact, this is your bus bar, right? So bus bar is nothing but this is a we can see it in if you have visited any substation, you might have seen that there is bus bar arrangement where the incoming and outgoing feeders are connected. So the incoming feeder gives supply, power supply, and through the outgoing feeder we take the supply. And in between we have various connections with the transformer, etc. And we can see here that these are the incoming feeders, in fact, right? I in 1, I in 2, and I in N1. So here there are N1 number of incoming lines, and here we have the outgoing lines. They are called N2 number of. So N2 number of outgoing lines are there. So in fact, the protective zone of the bus bar is this, right? In fact, when the bus bar is connected, if we'll see the structure, suppose we have this kind of arrangement, and so this is how the lines are being protected, right? So at both the end we have circuit breaker and relay arrangement, which in fact protects the line. And if we'll see the protection zone of the line, in fact this is your protection zone, right? This is also connected somewhere, this is also connected, and for this line the protection zone is this, in fact. Okay, so then we can see here that we'll see somewhere it will be here, right? Okay, if we'll see, this is the bus bar. Now this bus bar is being protected by the protection zones of the lines. In fact, if we'll say it is line 1 and it is line 2, then we can say that this bus bar is protected by both line 1 and line 2 protection schemes, and they are in fact overlapped, right? But in fact they will act as the backup protection for the bus bar. It will not act as the primary protection scheme. So therefore, because as the system is advancing more and more moving towards the more and more high voltage system, and when the short circuit happens in the bus bar, exactly, right? So the short circuit level becomes very high. Right? Short circuit level becomes high. Therefore, it is very, very essential that as soon as there is a fault in the bus bar, the bus bar needs to be isolated from the other part of the system. So we can say that there is a large concentration of short circuit capacity at bus bars, and a fault on the bus bar, though rare, it is very rare, but causes enormous damage. If the fault happens, in fact it causes lot of damage to the substation. When the protective relays operate to isolate the bus bar from the system, there is a large disruption to the loads. In fact, because you can see here, a bus bar is connected to many number of lines, incoming and outgoing lines, and if the bus bar needs to be isolated, then the supply will be interrupted, right? So the causes of faults experienced on bus bars are because of the following: because of weakening of insulation, because of aging, corrosion, because of the salty water. Therefore, most of the time we saw it has been observed that in the coastal areas, in the substations, the bus bars become corroded most of the time, and breakdown of insulation because of the over voltages, foreign objects, and so on. And there are also many agents, they in fact work behind these faults. For example, the rodents, lizards and snakes, and they in fact cause busbar faults in remote unmanned substation. So what form of protection is best suited for the busbars? So a little reflection, we can see what kind of protection is in fact suits. A little reflection will convince the reader that the differential protection will suit this situation best, because the ends, the terminals of the system are physically near to each other, because differential protection scheme is used for an equipment or for a system where both the ends of the system is very they are located near to each other, they are not far from each other. Like both the ends of the system, they should be located near to each other, right? And under that condition, your differential relay works very nicely. So let us see the differential protection of busbars, and you can see here that we have a busbar and we have 3 lines connected in this busbar, 2 incoming lines and 1 outgoing lines, and each of the line is rated at 1000 ampere, the incoming lines 1000 ampere and 2000 ampere, and the outgoing line is rated at 3000 ampere, because the sum of the current of the incoming has to be outgoing in the outgoing line. So now the question is, how will arrange the cities, or how will take the city ratios in fact, so that it will work very nicely. So certainly if we will see this, we can say that this will be 1000 is to 1 ampere, this will be 2000 is to 1 ampere, yeah. This will be 3000 is to 1 ampere. So in fact we will tell this, right? Already it is there, no need to write. So now you can see here, this will be our certain intuition that we should take these ratios. But now if we will analyze, will it work in fact properly? Let us see it. So 1000 is to 1, if we will see, it will be 1 ampere in the secondary of this city, and here also under normal load condition, if we will take 2000 is to 1, so 1 ampere will flow over the secondary side of this city. So the net current will be here 2 ampere, right? 1 ampere, 2 ampere. Now here if I will put one city of ratio 3000 is to 1, then the current here it will enter 1 ampere, right? So now 2 ampere is coming and 1 ampere is going out, and rest 1 ampere is going through the spill path, that is through the overcurrent relay. So if the clock setting it is at 0.5 ampere, then obviously this overcurrent relay will give the trip signal, right? So that means it will maloperate. So therefore, so what kind of city ratio we need to choose? If suppose I will say I have cities with 1 ampere rating, that is the secondary side current of the cities are 1 ampere. Now how I will choose? In fact it will not work. And then how I will choose? Then I will choose in such a way that your spill path current should become 0, right? Now if I will choose 3000 is to 1 for each of the cities, right? For each of the cities, for outgoing feeder as well as incoming feeder, then you can see here it will become how much current? Now it will become 1000 by 3000, 1 by 3 ampere, and it will be 2 by 3 ampere, right? and the net current will be here 1 ampere, and similarly here 3000 is to 3000, so it will be 1 ampere. So now the current through the spill path will be 0, right. So that means what is the conclusion? The conclusion is that the CT ratio should be chosen in such a way that it should match with the maximum current carrying feeder or maximum current carrying line, right. So that means I can say that the CT ratio for all the CTs in bus differential scheme will be maximum out of all the feeder currents. This is your maximum current, right, divided by 1 ampere or 5 ampere, whatever the secondary current rating may be. Maybe it will be 1 ampere or maybe 5 ampere, right. So therefore always we need to choose maximum out of all the feeder currents, whether it is outgoing or incoming, it doesn't matter, but the maximum current needs to be chosen. Okay, let us see how the differential scheme in a busbar protection, how it will behave towards the external and internal fault. So if we will see the fault, external fault, let us say, right. So now this is a busbar protection scheme, differential protection scheme for a busbar, and if we will see it now, let us see it. You can see here. So this is a busbar where the incoming feeder has 10,000 ampere and 20,000 ampere, and the outgoing feeder is having 30,000 ampere rated, and the CT arrangement is made 3000:1 for each of the CTs, right. Now suppose the external fault is happening here, and so let us say because of the CT shape, because if we will see the fault current here, external fault. So for external fault, because this is a single feeder, so the total current will be 30,000. So the highest current is passing through this CT, right, and 10,000 and 20,000 is passing through this, though these CTs are of the same rating, right, and this CT is becoming overburdened, and because of that the CT core becomes saturated, right. So saturation happens here into CTC, right, but CTA and CTB will be operating in normal condition, and because of the saturation, say let us say that 4 ampere current is flowing, okay, because of the saturation, and in the secondary side, because most of the current then will pass through the magnetization path, we'll see how it is, and therefore the relay will, through the relay in the spill path 6 ampere current will flow, and which will trip the overcurrent relay, right. So therefore for external fault, one of the CT will become overburdened, and because of that, maybe because of that the current will pass through the spill path. So because which line will be overburdened, that line in fact the CT installed in that line in fact becomes saturated, right. So now we can see that the figure shows currents during an external fault beyond CTC. So here is the external fault. It can be seen that CTC, the CT on the faulted feeder has to carry the sum of the currents fed into the fault by various feeders. Therefore CTC sees the substantially large primary current than either CTA or CTB. In all likelihood CTC will therefore become saturated, right, because it is carrying the largest primary current. So we can therefore no longer assume that CTC will faithfully transform the fault current. So therefore we are assumed here that CTC becomes saturated. We will see it in the next slides how it becomes saturated. Okay, now if we will see the internal fault, so let us see the internal fault. So with the internal fault, what happens? All the CTs, they in fact provide the current from each side, right? Because here I think it is a single faded line, so therefore only the current is flowing from this side, right? And this side the current is 0. So therefore for the internal fault, CTA and CTB will work very nicely because they are providing 10,000, 20,000 ampere each if the internal fault current is 30,000 ampere, and CTC is providing 0. Even if from CTC, if some source is there, it would have provided 30,000 ampere, not 30,000 ampere exactly, some current, yes, 30,000 ampere, maybe contribution to the internal fault, not exactly 30,000 ampere, right? The contribution from all sides will be different, right? So therefore, because here we have considered a single faded line, so therefore CTC will provide the 0 current and all the CTs will function very nicely. So the mal-operation of the busbar differential scheme on external faults is caused due to the non-ideal behavior of a CT carrying excessive primary current. It will therefore be pertinent at this point to take a closer look at the actual behavior of the protective current transformers. So let us see the actual behavior of a protective CT, right? This is in fact your CT. Here the primary current is flowing, right? And your secondary current, and we are showing here the equivalent circuit is being shown with the primary parameters referred to the secondary side. So RP dash and XP dash, they are the referred primary and primary resistance and the leakage reactances to the secondary side, and your RO dash and XO dash, they are the referred magnetization resistance and the reactances, right? And similarly your RS and XS, they are the secondary winding resistance and XS is the leakage reactance, right? So now if you will see the current with CT ratio n is to 1, then the current here, because this will act as ideal transformer, therefore it will be IP by n, and your magnetization current IO will depend solely on ES, right? So whatever value of ES will be, and the value of ES will depend upon the current passing through this, right? Okay. So ES is the current across this magnetization branch, and if we'll see, this will be your equivalent circuit now. Now in equivalent circuit of the CT referred to the secondary side will be here, we can say it's a current source having value IP by n, and your equivalent circuit becomes RP dash XP dash RS XS, and IS will be obviously IP by n minus IO, right? That is IS. That is the exact secondary current flowing through the burden. Okay. Now if we little bit more simplify this circuit at the secondary side, then I can say IS as a current source, which is equal to IP by n minus IO, and it is flowing through the burden. Okay. So when this current is flowing, right, it will depend upon this ES, right? And if you will see this relationship, your flux will be equal to Es by 4.44 Fn, right? F is the frequency and N is the number of turns. So ES is varying based on the current in the burden rate. So as your flux will depend upon this parameter ES. As your ES will increase, your flux will also increase, right? Okay. So therefore, when your external fault is happening and IS is increasing, right? So as the primary current is increasing, so your secondary current is increasing, and by that way your ES is increasing, leading to increase in the flux, right? When the flux is increasing, so we know the BH curve already, we have discussed this, that as soon as the flux is increasing, it requires more magnetizing current in order to provide that flux. So you can see here, this is your knee point, and as soon as the flux increases, your magnetization curve, you can see it gets saturated, right? And little further increase in the current, little further increase in the flux will lead to the high magnetization current, right? Here we can see high magnetization current, right? So therefore this current, this will be certainly increasing in nature, and this is in fact peaky in nature. It is not a sinusoidal current, right? Not sinusoidal. So therefore this is very high value of current, right? And this is your flux waveform. Now we can see the waveforms of primary current, then magnetization current, then your flux rate. We can see here that this is your primary current, and your magnetization current becomes little peaky, so it is not a sinusoidal current. But your flux becomes, it is changing at the zero crushing, but it becomes flat as soon as your magnetizing current becomes peaky. Your flux, because of your flux gets saturated, right? So therefore your flux becomes constant, right, at this point. Okay, so now if we'll see the induced voltage ES, so your induced voltage will, again it will become like this, right? Because when your flux is changing during zero crushing, it has certain value. If we'll take the derivative of the flux, it will be like become a constant. But when the flux is remaining constant, your induced EMF will become 0, right? So therefore your induced EMF and your current will be, secondary current will be ES by R burden. So therefore it will become highly distorted, right? As soon as your core becomes saturated, right? So then your ES and IS becomes distorted. Previously, initially when it starts, up to the saturation point, your ES and IS remains fine, but as soon as it gets saturated, then it becomes highly distorted. It becomes a square wave. Instead of a sinusoidal wave, it becomes a square wave, right? So now if we'll see the circuit model of a saturated CT, so how it looks in fact. So this is your primary current and this is the reflection of primary current. And now in the magnetization path, it will be very high current will flow under saturation condition. So therefore your IO will become IP by N in fact. approximately it will become equal to IP by N, and your secondary current will become 0. So because as the high current will be drawn in the magnetization current because of the saturation, so the current flowing through the burden will become 0 gradually, right? Okay. So now we can see this is the same aspect, just it is modified just by the ideal transformer is being replaced by a current source, that is IP by N, right? Okay. So now let us consider the external fault with one CT saturated, right? So how it will look like? So just replacing the equivalent circuit of the each CT. So this is just drawn, this figure is drawn considering the secondary side equivalent circuit of the CT, right? That is, all the parameters refer to the secondary side of the CT. So this is in fact for CTA, this is for CTB, and this is for CTC. And now some external fault is happening outside, opposite beyond CTC, and here we can see these are the current sources, because secondary side when we convert it becomes IA by N, it is IB by N. Now because CTA and CTB, they are not saturated, so therefore the magnetization current will be IOA here and here IOB, and as the CTC is becoming saturated because of the external fault, right? So therefore it will become short circuited, right? And no current will flow here in the burden, right? So now you can see that this is your relay which is connected in the spill path, that is overcurrent relay. Now if we will see the net current here, it will be IA. So let us consider first what will be the current flowing through this, and this will be IA by N plus IB by N, it plus, sorry, here it will be minus IOA plus IOB, right? So this will be your current passing through this, and now because it is short circuited, right? So therefore some current will flow through this and some current will flow through overcurrent relay when this stabilizing resistance is not there, right? So now without stabilizing resistance we are just analyzing. Now because of this spill path current, this relay will trip. Now in order to avoid this tripping, so how we can avoid this tripping? Just by connecting one resistance on the spill path, which we call the stabilizing resistance, which will in fact resist the current flowing in the spill path, right? So then your current through the overcurrent relay in the spill path will be reduced, and it will become less than the pickup current. So then we can say that to the external fault your relay is not responding, right, even if your one of the CT is becoming saturated, right? So therefore that is called the high impedance busbar differential scheme. So when we are putting a high impedance or high resistance in the spill path in series with the relay, that is called the high impedance differential scheme. In fact it protects to stabilize the maloperation of the relay during the external fault. Okay. So let us see external fault with one CT saturated, and if we will see this voltage, what is this voltage across the relay and the stabilizing resistance, then I can write that V set will be equal to the current, the net current into Zs. So Zs is your stabilizing, Zs is your secondary side, CT secondary side impedance, right? Okay. So now it will be this, and this will lead to R stabilizer. If we will find R stabilizing, right, if we'll find this, so we can say that your R stabilizing should be, how I will find R stabilizing, this equation how I will find, I will just write that your V set by I power unit, it should be your it should be greater than equal to R stab, right? Okay. So that means your R stabilizing value or stabilizing resistance value should be in such a way that this V set by I power unit. Okay. So if you will see this figure again, your V set by I power unit will give us a resistance value that should be greater than R stabilize in order to stabilize this differential scheme to the external fault, right. So if you will see this equation, and it should satisfy in fact this equation, that your V set by R stabilizing, so it will give a current through the spill path, and that current should be less than equal to I power unit, and from this equation we will find R stabilizing should be greater than equal to V set I power unit, right. This is not less than equal to, this is only less than I power unit, right, and this will lead to I stabilizing greater than equal to V set by I power unit. And in fact we know that if we have n number of lines connected to the bus, you can generalize the formulation, and your V set will become in fact Ik by n. N is your CT ratio, right, and K is your number of it will indicate the index for number of lines. So K is varying from 1 to n minus 1, Ik by n sum minus n minus 1 IO. So if we will say that your magnetizing current for all the CTs are 0, all the CTs are equal to IO, right. So then I will say that n minus 1 into IO into ZS. So that will give me V set, that is the voltage across the spill path, and where this is the maximum external fault current, right. This is exactly equal to your maximum fault current up to which the differential scheme remains stable, right. So this is your maximum external fault current. Okay. So now therefore neglecting the magnetizing currents, we can write that your V set will be equal to, just by substitute, this is your maximum external fault current, right. So I can just substitute this as maximum external fault current, right, and neglecting this magnetizing component, magnetizing current, I can write V set equal to, the preceding equation gives the value of maximum external fault current up to which the differential relaying scheme remains stable. So from this equation we found V set, V set is calculated from this, right, from this equation, and it is in fact generalized here in this equation, right, V set. And after finding V set, if we just neglect the magnetization current in that formulation by substituting the external maximum fault current, then from this equation we can find the equation for maximum external fault current, which will be in fact, which will be for which the relay in fact remains stable, right. So that value in fact gives the maximum external fault current for which the relay, that is this stabilizing impedance differential relay in fact gives the stable operation for this maximum external fault current. Okay. So now we will calculate the minimum internal fault that can be detected by the high impedance busbar differential scheme. Minimum internal fault that can be detected by the high impedance busbar differential scheme. So, high impedance differential scheme is this, and the CT ratio chosen is n:1, n:1 for all the CTs, right, and we need to find the minimum internal fault current. So, that is minimum internal fault current which is required to, which can be detected by this high impedance differential scheme, right. So, already we know that this V set will be how much? IF min secondary, because the current flowing through this is secondary side of the CT. So, it is mentioned IF min secondary into R stub, right. So, this will be V set voltage across this spill path, and from this equation I can find IF minimum secondary, that is internal minimum internal fault current at the secondary side will be V set by R stub, okay, R stabilizing, and from here we know that V set by R stabilizing is nothing but is equal to I per unit, right. So, therefore, I can say that IF min, that is minimum internal fault current in the secondary side is equal to the pickup current, right. So, then I can just substituting the previous figure with the equivalent circuit model. This will be your equivalent circuit model with different parameters, right, neglecting the leakage reactances, right. Leakage reactance is neglected, okay. So, now your RL is the burden, okay, and RS is the secondary side CT resistance. Now, this is for CT A, this is for CT B, and this is for CT C, and if we will write the equations, now your IF minimum, that is minimum internal fault current at the secondary side, which is equal to I per unit, I can write it as IA by N, right, IA by N minus IOA. So, this is the current IO by N minus IOA, right, and plus IB by N minus IOB, this current, and IC by N minus IOC, this current, right. So, from all sides the current will flow. So, therefore, your net current, your IF min secondary, that is equal to I pickup, will become equal to this, right. So, now this current IA plus IB plus IC by N minus IOA plus IOB plus IOC. So, this current is nothing but your internal fault current at primary side. So, internal fault current at primary side is IA plus IB plus IC, right. So, therefore, I can substitute IA plus IB plus IC as internal fault current at the primary side, which is reflected in the primary side, divided by N minus 3 IO, which is nothing but equal to your I per unit, right. Okay. So, then I can write that this, if we assume that IOA equal to IOB equal to IOC equal to IO, then I can write the above equation, that equation as Ni per unit, Ni pickup equal to IF internal minimum primary, that is the internal fault current, minimum internal fault current at the primary side, minus 3 NIO, right. So, from this equation I can find the expression for minimum internal fault current at the primary side, which is equal to N times I pickup, what is the pickup current, plus 3 IO. IO is your magnetization current in the each of the CTs. It is assumed that all the CT have equal magnetization current. So, with 3 feeders terminating on the bus in general, so this is for the 3 feeder network, which is where in a single bus the 3 feeders are terminating, right. So, in general for n feeders, terminating at a bus, we can have the equation for a minimum internal fault current at the primary side, that will be equal to n times I pickup plus small n times IO, right. So, where n, capital N is your CT ratio, right, this is your CT ratio, and your small n is your number of CTs, total number of CTs. Okay. So, now this current, this minimum internal fault current, which is detectable by the this stabilizing resistance bus differential protection scheme, is the expression for this is that, right. So, the expression for the internal fault current, minimum internal fault current, which can be detected by this scheme, by this stabilizing differential protection scheme, stabilizing resistance differential protection scheme is this, right. Okay, now if we will see the stability ratio of high impedance bus bar differential scheme, right. So, that is sorry, previously I mentioned this high impedance bus bar differential scheme as stabilizing impedance bus bar differential scheme. In fact, it is known as high impedance bus bar differential scheme, right. So, stability ratio of high impedance bus bar differential scheme will be like this. Already we know the stability ratio is defined as the external maximum fault current for which the relay mal operates divided by the minimum internal fault current which is detected by this relay. So, this is the stability ratio formula, and if we will substitute this IF external maximum, we know that already we have already we have derived, this is N V set by ZS, and IF internal minimum primary, we know this is N I per unit plus N IO, right. So, by substituting these two expressions here in stability ratio, we can easily find the stability ratio. Okay. So, this is all about your bus protection scheme, and in the next class we will also continue bus bar protection scheme, where we will a little bit we will talk more about this protection scheme, about the stability of this high impedance bus bar differential protection scheme, and also simultaneously we will talk about the generator protection scheme. So, thank you very much, thanks a lot.